All right, this is tutorial 3 on parabolic mirrors. Focus is going to be on equations to help us predict image properties and then look at the array diagram for a convex mirror. So I'm not going to derive the mirror equation, but it can be done through some clever geometry by looking at the array diagrams and where the image forms depending on where the object is located relative to the mirror. So I feel bad that I'm not doing a derivation for you. But let's just get into what it's telling us. So it's an unusual equation, and that's also the reciprocal. And in the previous tutorial, I had used a D for distance. I guess in the AP they use an S. It switches back and forth. IB might use a D. So basically it's this. You take the reciprocal of the image distance. So S stands for distance, and I is image. And you add to it the reciprocal of the object distance. It's going to equal 1 over the focal length of the mirror. So if you wanted to solve for focal length, you could do a common denominator, and this actually can be helpful in a few problems with multiple choice. I don't have much space here, but if I were to solve for f, right, my common denominator would be SI and SO. It would be SI plus SO all over the product of SI and SO. So you can jot that down because that's a handy little thing, because it tells us that the focal length is directly, well, it's actually a complex relationship. I can't say it's directly proportional to image distance or even object distance. Okay, a few things. This is one to keep in mind. So image distances, or object distances, regard either one, how do we measure them? What do we measure them relative to? So 0 is always where the mirror is. In front of the mirror is always a positive distance, whether it be an object or an image. So therefore, behind the mirror, the distance is negative. So if you go back to when we are inside the focal length of a concave mirror and we know the image form behind it, that means the image distance is negative. So when you go do problems, you've got to be mindful of that. Secondly, all right, so there's a magnification. So magnification, capital M, is defined as the ratio of the image size divided by the object size. All right, so that's the definition. So if my image is 3 times bigger than my object, my magnification is 3. And I'm going to put an absolute value sign there, because we're going to see that in our calculations, if you invert the image, okay, which many times happens with a concave mirror, your image size is going to come out to be negative. So we want to take the absolute value because we don't want that to influence our magnification. You don't have a negative one, a value of that. Now, a nice way to relate this is we can relate the ratio of the image height or image size to the object height to where you place the object. So again, we're not doing a derivation, but that turns out to be equivalent to the image distance divided by the object distance. And again, the absolute value, because you can have negative image distances. You can't have negative object distance. You can't place an object behind a mirror and expect an image to form. So a useful way of doing it is this one. How we can, if I know where I place an object and I figure out where the image is based on this equation, then I can get an idea of what's going on. So a negative image height, and I mentioned that before, when you go to solve it, especially with these problems, is real and inverted. The inverted part is a negative, and if it's inverted, it must be real. Okay, so let's do a problem where we're going to use our array diagrams and then we're going to use equations to verify. So we've got a concave mirror. Center of curvature is 30 centimeters. Is 2 meter tall object, so that's the object height. It's placed in a position of 10 centimeters. Okay, so there's our image distance. Okay, based on array diagram chart, approximate location. I don't know what I'm trying to say there. Find the approximate location. It's the size, orientation, and type of image. Okay, so where is our object? I'm sorry, I got that. Got to read more carefully. That's the object distance. Okay, it's placed 10 centimeters in front of the mirror. So in order to understand from an array diagram what kind of image we're going to get, we have to know where this is relative to C and F. So if C is 30, and therefore, we can infer F is 15, because F is half of C, and we're at 10, so that's important. So we know we're inside of F. And for inside of F, if you look at the chart above, I've erased mine, we know that the location is going to be, I'm just going to put as a negative image distance. It's going to be behind the mirror. We expect the image to be magnified. We can't say for certain what the magnification is, but we know it's going to be magnified. We know the orientation is going to be upright, and we know it should be virtual. Okay, so let's see if the equations verify that. So what we would say is, I want to find the image position, so I'm just going to solve for that directly. That's 1 over the focal length minus 1 over the object distance. So the focal length is 1 over 15 minus 1 over 10. I'm going to just do common denominator, which is 30, so that's equal to 2/30 minus 3/30, which is equal to negative 1/30. Okay, so therefore, the image distance, I got to remember that I would take reciprocal, is negative 30 centimeters. So negative 30 centimeters is exactly what we predicted. It is behind the mirror, so we know it's virtual. Okay, so now let's look at the magnification. So the magnification, which is by definition image height divided by the object height, is also equivalent to SI over SO, the absolute value. So that's the absolute value of negative 30 over 10, which is 3. Okay, so we get a magnification of 3, which is consistent with the idea that it's going to be magnified. Again, since we have, I just want to reiterate, since we have a yeah, I was talking about a negative image height, but I guess that won't work out with a... So our image height, right, HI, is just going to be the magnification times the object. So it was, I think it was 2, so that's going to be 6 centimeters tall. Technically, I mean, it's 6 centimeters tall, but if we put a negative in there, that supports the idea that it's going to be, I shouldn't say it's not going to, no, I'm saying it's negative, my bad. It's going to be upright. Okay, the key thing here, though, in predicting this, because these are the type of things you got to know, is when I figure out the focal length, either given directly, and where the object is, I got to ask myself, is it inside of F, between F and C, at C, or beyond C? Then you can get an idea of what based on a chart, where the image should form and what it should be like, and the equations will verify that. So let's finish up with a convex mirror. I think in the first tutorial, one of the first tutorials, not for parabolic mirrors, but for images in general, we talked about what generally happens with a convex mirror when you have light from a distant source comes in. And the important thing is it does the exact opposite of a concave. Where concave converges light, this diverges light. Okay, light never comes into focus. And again, it's following the law of reflection. Like if I draw a normal to that surface, to the mirror there, you can see that I've kind of followed the law of reflection. So we can never expect a convex mirror to form a real image. We can never expect it to form in front of the mirror. We can never expect it to be upside down. Okay, based on what we've learned from previous situations. So let's show formally how we form an image. This is a little bit more abstract. So the two rules that we're going to apply are similar to the one for concave, but they're kind of inverted. And then maybe inverted is not the right word. All right, so let's talk about this. Parallel rays come in. So if I draw a parallel ray coming in, because that's always easy to do. Let me try that again. All right, this is not going to behave. Let's see if I can delete. Yes, I want to delete. Okay. All right, I'm going to just forget about that. I don't have time to stop. So if I come in, I got to love this thing. Parallel. It's not going to reflect through the focal point. It can't. It's not a converging mirror. But it reflects as if it came from the negative focal point. So you're going, what's a negative focal point? Well, it's the opposite. So if this is the focal point of a concave, the negative F would be inside of the convex mirror. So what I'm trying to say here is if I just draw a reference line from the focal point to that mirror, that's how the ray will reflect, as if it came from there. And that's consistent with the idea of it's diverging. So I know that the image has to be somewhere along this red line. My eye is out here, remember. Okay, so I just need something to intersect with that. And so that's the next rule. Rays headed towards negative f. So I'm going to try to use this once again. I'm going to try to get this close. So I'm going to kind of head towards negative f, but I clearly can't get there because the mirror gets in the way. So let me backtrack a little bit. But if I were to continue that line, that's where it hits the mirror, or pretty close. That's going to reflect parallel. So in the concave, if you go through f and hit the mirror, it goes out parallel. Here, if you head towards negative f, hit the mirror before you get there, it's going to come out parallel. All right, I know I'm mixing colors here. So I've got two reflected rays. Let me draw this red again. This one and this one. They're clearly not going to meet out in front. We anticipated that. So where does your eye think that those rays came from? Well, hopefully you learned your lesson from the two previous examples with a plane mirror and being inside f of concave. It traces it back to a common point, not at the negative focal point here, but right around there. So it's above the optical axis, so there's my image. And what can we glean from that image? Well, it forms behind the mirror, as we expected, so there's a negative image distance. The size is always reduced. Okay, you'll never ever get an image behind or from a convex mirror that is bigger or even the same size as the object. It is always an upright orientation and is always virtual, because virtual and upright go together. And so if you look at all the possibilities you can get for an image, if you want a magnified real image, you have to be in front of a concave mirror. If you want a magnified virtual image, you have to be in front of a concave mirror, but inside of f. If you want a, a real image that's the same size, you got to be in front of a concave at C. If you want a virtual image that's the same size, you got to be in front of a plane mirror. If you want a smaller image that's real, you have to be anywhere beyond f of a concave. And if you want a upright diminished image, you have to have a convex. So there's no overlap in properties from the mirror's placement. We've covered all the bases, just doing it in different ways. So you kind of want to understand that. All right, so, oh boy, there's more here. What is the location and size of a 2 centimeter object placed 10 centimeters in front of a convex mirror if it has a focal length of -10? So I want to point out, the focal length for a convex is -10. So location, that's SI. So 1 over SI equals 1 over F minus 1 over SO. So F is 1 over -10 minus 1 over 10. Okay, so let's see, I think that is equal to -2/10, which makes SI equal to 5, okay? So, nope, I'm sorry, -5. That makes sense. It's got to be behind the mirror. And then the magnification is going to be SI over SO. And that's 5 divided by 10, which is 1/2. So we get what we expected there. All right, in the minute and a half I have left, let's talk about applications of parabolic mirrors. Okay, it collects. They're very, very useful. Boy, I haven't looked at that, so. All right, I will talk to you about that in class because, actually, let me pause this. Okay, so concave mirrors can collect signals for satellite dishes, right? If you have a satellite dish to watch TV, you notice that they're concave in shape. And perhaps the most important thing I have here is for telescopes. All telescopes collect light, at least the modern telescopes, by using parabolic mirrors. And there's so many more advantages to that over lenses, which we'll talk about. You can also use it for sound. It can collect sound for parabolic microphones. You may have seen those before. And you can think of spies, or you can hear a conversation very far away by collecting the sound as it hits the microphone at the focal point. and all the light or all the sound will converge at where you place when you place the microphone at that point. You can create beams of light for flashlights and headlights. So it's the reverse of what I was talking about. Place the light at the focal point and come out parallel, you get a beam. Okay. Yeah.